All right, welcome to CS50. This is the end of week 5. So I felt that Monday's lecture kind of fell a little flat. I wasn't really feeling it. So I thought we'd try to spice things up perhaps today with some props. So I went shopping there in the square. But first, some good news and some bad news. Which would you like first? OK. I heard one person say good first, but then everyone else wants the bad news. OK, so bad news. Quiz 0 is next Wednesday. But this is mitigated by the fact that there's no class Monday, and there's no problem set next week as well. So realize you have a handout in your hands from outside that describes all of the particulars for Wednesday's logistics. Do not come here. Because of our size, we'll split up into 3 different lecture halls where you actually have a decent writing surface for the quiz. So that's all there, and it's also on the course's website. If you lose this piece of paper, or if tuning in afar do not have this piece of paper, it's under the quizzes page. Also on the quizzes page are 5 previous quizzes along with their solutions. I know this is probably more interesting than the quiz, but OK. Oh, and actually the segue here was this is a wonderful way to waste a lot of time. Not only was this implemented years ago, actually, in ASCII or ASCII art, which this is a complete tangent, isn't it? So this was implemented in ASCII art, the relevance of which is that we kind of used ASCII art for last problem set for the game of 15, but we definitely raised the bar a bit with Sudoku, where you're actually using a graphics library called ncurses, albeit a very limited graphical library. So this thing used to live on a server that you could telnet to. Telnet is kind of like SSH, but it's unencrypted. So this guy years ago just made like this whole animation of Star Wars, and now there's variants on the web and in Java applets, but it's pure ASCII art for almost the entirety of that movie. So we'll link to that on the course's website if you're curious. It's like an hour or more long. Now back to reality. Let's see, we were on the bad news. So the bad news, the quiz 0 is Wednesday, but there's innumerable resources on the course's website under quizzes from past quizzes. Realize that the material does vary somewhat year to year. So if you see some topic that's completely over your head, it may very well be that it is completely over your head, but we might not have covered it either. So do consult the syllabus or me or a teaching fellow. And then also this week on Sunday, Monday, Tuesday, the sections will ostensibly be review for the quiz. And then this Sunday at 7 p.m. in Emerson 108 will be a course-wide review, which is optional, but you're welcome and encouraged to go. It will be filmed and put online by Tuesday, and this will supplant the regularly scheduled walkthrough. So there's no walkthrough this Sunday. There's instead a review for this, and all of that is on that PDF for your reference. OK, so let's see. We did the good news, no PSET, no lecture on Monday, which means this is the last time we'll see you for a week. But without further ado, some stuff. So on Monday, we talked about pointers. And we've been talking about pointers. And this is really the last piece of interesting or, dare say, complicated syntax that we're going to introduce in the context of C. Because once you have this ability to manipulate memory really at your will, you can do a lot of interesting things. And also, thus far, we've not really had very useful data structures. You've had these things called primitives. And a primitive is an int, a char, a float, any of those little things that you get for free in the language. And then we kind of have this data structure called an array. But it's really just a nice conceptualization of a chunk of memory back to back to back to back that you can address via that square bracket operator. But today we introduce a fundamentally more interesting data structure, and it's more of a traditional data structure, or as people call it, an abstract data type, ADT, if you ever see that acronym somewhere. And that just means that in general, these more interesting data structures are things that have data associated with them, properties, fields, call it whatever you want, pieces of information, variables, much like the structs that we've discussed have, but they also have operations related to them. So the thing about C is that even though we have these structs that we started using on Monday, just to encapsulate some related information, those of you who've tackled PSET 4 know that all of our global variables, we just kind of tucked inside of a struct just because it felt a little cleaner to encapsulate them. And this word, encapsulate, is actually a theme in programming because it means to gather together like or related data. But there's no fundamental operations that are supported by that struct, right? There's no functions related to Sudoku's board. Anything you do with g dot whatever has to be done very manually. G dot x gets some value, G dot y gets some value. You don't have any built-in mechanisms. But now that we get to start talking about these things called linked lists, which will redress some weaknesses in arrays, can we actually say that there's some formal operations, some features of these data structures that up until now we haven't really had? But why care at all? Like, why not just draw the line after arrays? Well, arrays are only so good. What is a downside in your mind already, perhaps, about arrays? OK, and let's actually, since it's not been working very well in past lectures, I felt where there's just some murmurings and then I fill in the blank with my own answer. So give me a hand if you would, because it's hard for me to hear you. OK, black shirt here. Yes. Oh, you're wearing white. Good. So you need to know the size of the array that you want before you create it. And there's a couple of ways we can create arrays now, right? One is just to declare it statically within some function, or maybe globally, but statically in the sense that you say int, then the name of the array, open bracket, some number, close bracket, semicolon. Or maybe it's 2-dimensional or 3-dimensional, but you have to know in advance what that size is going to be. Or you can also allocate an array dynamically, which means on demand, using what new function or what useful feature of C? So malloc. And malloc doesn't give you an array per se. It just gives you a pointer to a chunk of memory that is as big as you ask the operating system for. But in the event that the OS just doesn't have enough memory to give you, you ask for 5 gigabytes. And that's just unreasonable. What will malloc return? Quick review. So it's going to return that null value. And so the best lesson you can sort of hammer into your head when playing with problem set 4 and 5 and beyond is anytime you manipulate pointers in C, constantly, very defensively check for null pointers, because otherwise these very bad things known as seg faults happen a little too often. So arrays require that you know in advance how big they are, and that might be fine because we already saw in that silly little registrar example that I did where I inputted students' names and houses and ID numbers. Well, I can just change the constant called students from 3 to some other value. So why is that not really a compelling argument that, OK, yes, you have to declare array's size in advance, but you can always change it? Like, what is the downside about that approach? And recall, in that example, there was sharp define students, and then it was hard-coded at 3. But I could very easily change that, right? That was the whole point of the constant. So why is that really not a compelling, argument in favor of arrays? Yeah. OK, so causes security vulnerability. So the fact that arrays are fixed length and you, the programmer, have to check the length of them, that's the security vulnerability, sure. But specifically with regard to their size, why can I not just say array size can be changed, just change the constant in your code? Because the user can't. Right, so the user can't do that. You, the programmer, absolutely can go into your .c file or .h file, change that constant, but then what do you need to do? Recompile, right? And that's not that compelling, right? Maybe now in CS50, week 5, it's pretty easy to recompile. It's pretty fast because we're only writing so much code. But, if you're Microsoft, you're any company that's actually written a program and ships it in a shrink-wrap box, or a user has downloaded it, like, there's no chance thereafter to actually change anything in the source code unless you update the whole darn thing. So we need some more dynamism. So malloc does give us that, because we can ask the user how many students are in the class, and then we can allocate using malloc a chunk of memory that's actually big enough. But what happens if I start up my program and I say, I have 100 students this semester. All right, so give me enough memory for 100 students. So 100 times the size of a student struct. OK, but then what if there's some late registrant at the university, right? And this happens in every course here. People add, they drop, but after the program's already running, after the program's already compiled. So I now have an array of size 100. What do I then do if while the program's running, I need to change its size? What are my options? I mean, intuitively, what would you just like to do? Right now I have 100 students in an array, but now I'm out of space. So just intuitively, what would you do? Make a new array, right? So use malloc again. Use whatever technique you used the first time. Make a new array. Maybe err on the side of safety. Make it 200, even though you might waste some memory. And then what do I do? Now I've got an array that's 100, an array that's 200. What do I do? So copy one into the other, and that's a simple for loop, while loop, whatever you want to use. And then what should I do? So free the first array, right? And you can do this in relatively few steps, right? We just rattled off maybe 5, 6, maybe max 10 lines of code to call malloc again, to use a loop to copy the contents of the old array into the new, and then to call free on the original array. But what do I probably need to keep track of now, right? Arrays are just a chunk of memory. What do I need to keep track of if I've now added some more students to this bigger array? There's murmurings. What? OK, the size of it, right? So this is one of the downsides, upsides, however you want to view it, of C. The burden is on you to remember the size with some integer called n. All right, but this is kind of annoying. And we saw this ability in getString. So you might not recall the CS50 library source code, but you do have it. And it's, at this point in the semester, probably pretty accessible, reading it top to bottom again, at home. But our getString function did exactly this. We took a guess. We allocated, like, I forget what the constant is, 128 bytes, something arbitrary, but relatively big. And then we have a loop that says if the user types in a 129th character, let's call a new function. And we actually, slightly more fancy, used reallocation, which actually does that copying for you, so you don't need to resort to the for loop. But it was the same idea. But this is, arguably annoying. Every time you want to add something to the array, you have to check its length. If it's too small, reallocate an array. I mean, that's a lot of minutia just to add something simple to your array. So it turns out that there are data structures that redress this, right? If the downside of an array is that it's fixed size, well, why don't we craft a data structure that's of variable size that grows when we want it to, and we don't have to jump through all these stupid hoops of copying big chunks of memory again and again and again just because we didn't have the foresight to know in advance how big this thing needs to be. So we can express this data type, frankly, using just kind of a pretty clear picture. So if I have an array, it looks like this, and this is of size n, or in this case size 4. So I put a bunch of new students in here. We've got student 0, 1, 2, 3, but now I'm screwed if I want to add more students here. But this new data structure that we'll call a linked list and is much more compelling is something that might look like this. Well, when I have one student, let's allocate a student object or a student struct in C speak. Well, if I have a second student, let's create another one. Another student, let's create another one. Another student, let's create another one. And then inside each of these structs, just as in my example last week, I had an ID field, and I had a name field, and I had a house field, and repeat that for each of these guys here, I can do the same thing here. I can do ID, I can do name, I can do house, but because I've called malloc for each and every one of these students on demand, I need to somehow keep track of where they are in memory. Because when you call malloc, the stuff you get back, the pointer you get back, is not guaranteed to be back to back to back. Maybe by chance it will be, especially if you call it in rapid succession, because no one else is using that memory. But it's no guarantee. So what you get back every time you call malloc is a pointer to this thing, a pointer to this thing, a pointer to this thing, and again. And now we seem to have a downside. Arrays, previously, we could remember just by way of one pointer or by way of their name. But how many pointers do I need now to keep track of my 4 students? So it seems 4, right? Because I got back 4 unique addresses. They're not necessarily contiguous, which means I can't use pointer arithmetic. I can't use square bracket notation because that assumes, that requires a leap of faith that everything is laid out contiguously where it's expected. So I intentionally left this extra field here. So if we just are a little clever and define our student struct as having not only 3 fields that we really need, but a 4th field, maybe we can just string these things together. We can daisy chain them, if you've heard the word. So we have a pointer that, yes, points to the very first student. But you know what? We don't need 4 more pointers separate. Why don't we just include them in our struct and somehow link these things together in this fashion? And the only thing I have to be really careful about now is what? What goes here? So you need some sentinel value, which will probably be null in this case. Anytime you need sort of the absence of a pointer, null is important. If I hadn't done that, what might happen if I traverse this list as by in a for loop or a while loop, just following these pointers? And how you follow pointers we'll see syntactically today again. What could happen if this is not null, but it's just some unknown value, garbage values, as we keep calling them? A little louder. Yeah, you could follow a pointer that just so happens to look like a number, but really leads nowhere useful, nowhere you own, and so you get that typical seg fault. All right, so let's try to frame this specifically. All right, so this, I would propose, is a new struct that we use. And let's simplify. Let's not use student objects just yet, because there's a whole bunch of additional data, which feels a little complicated to keep track of. Let's rein it in. Just assume we're storing numbers, or just the IDs. So I'm going to use that same typedef feature before, because I want to call this thing a node. And so in general, anytime you have these graph-like structures, these list-like structures in computer science or math, they're generally called nodes. So we'll call this thing a node, using the same syntax as last week. But notice one difference here. Last week when I typedef something, I didn't say typedef struct name of the thing, then the curly braces, then the name of the thing again at the end. But in this data structure, notice how one of the fields, even though this is the student version, notice how one of the fields needs to point to an object of the same type as the thing storing this pointer. In other words, we need a way to be sort of self-referential. And this just means that using the syntax of C, if you want to store inside of a struct a pointer to that same kind of struct, you have to just append its name here, even though it looks somewhat redundant. So take it on faith for now that to declare a struct that has an int inside, familiar syntax. And if we want to have a pointer that leads elsewhere, we simply define this as struct node star next, although next could be called anything we want. So what does this mean specifically? This just means that I declared a structure that in general is going to look like this, where this field is called n, this field is called next, and the data type of this thing is what? Sanity check? That's just an int, and this thing is a pointer to a struct node. So a pointer to a struct node. OK, or pointer to a node, if we want to just simplify. All right, so let's take a look at what we can do with this and why we should actually care. So let me go ahead and make a thing called list1. This is the same printout from Monday, if you have your handout with you, or there's extras outside. I'm going to go ahead and run list1. And to demonstrate this use of linked list, I had to write a sort of quick and dirty program, because just coding up linked lists in no context really isn't that useful. But if I instead run this version here, what I decided to do was turn it into a little bit of an interactive interface. So what's just executed is my main routine. The main routine has some printf stuff, and it just prints out this quick and dirty menu where I just map numbers to different operations. So a linked list, as this picture will be generally called, has a bunch of operations that are kind of inherent to it or related to it. The things people like to do with linked lists is find things inside of them. So in this case, I might want to find an integer in the list to answer questions of the form, is this student in the list? Is this integer in the list? So that's find, otherwise known as search, or any number of other things. Traverse just means start at the beginning, go to the end, and maybe do something along the way, generally print things out. So that would be the traverse operation. Insert, as the word implies, just means add a number to the list. But here's where things will get a little interesting, because if you have this string-like structure like this, inserting can actually be kind of tricky in some situations, because if you want to keep this list sorted, which you probably do for efficiency reasons, as we've seen, so you can actually search it a little more effectively, you know, we might want to put the new student here. That looks like it's pretty easy. Update this arrow, update some other arrow in here. But if it's sandwiched in the middle, feels like there's going to be some more code and some more movement of pointers. If it's at the end, again, it's a different case. So this simple idea of inserting a number into a sorted linked list can actually be broken down into three cases, right? Beginning, middle, end. And hopefully we can generalize in that way. And delete, kind of the same thing. If I want to delete an arbitrary student or int from the list, I might have to treat the front guy a little differently from the end guy, just because they look different from everything else in the middle. So this is consistent with this idea we've been preaching of design. How can you break a problem down into its constituent parts? Well, there's like three cases: beginning, middle, end. And that's precisely what we'll do. So right now, my linked list, according to this program, has nothing in it. So I'm going to go ahead and insert by typing 3. It's going to ask me a number to insert, and I'll say 50. Enter. So list is now 50. So this is a very ugly, quick and dirty program. I just spit out what the list currently is. Let me insert another number. So let me go ahead and insert, let's say, the number 61. Enter. Program seems to be working. I've inserted 50, then I inserted 61, and maybe it was just appended, but hopefully it's actually been appended in sorted order. Let's try again. Insert 51 should hopefully end up in the middle, and yes, indeed. And we can continue along this way, and we'll insert one more for demonstration's sake, and we seem to have a running list that, if it's consistent with what we're talking about here, is growing and is growing and is growing. OK, so a very underwhelming program. We could have implemented this a week, 2 weeks ago, just using an array. But if I start inputting in enough numbers, as you pointed out, eventually we're going to bump into a hard-coded limit, at which point you have to do this, the somewhat annoying, somewhat time-consuming process of creating a new array, copying the old into the new, and then repeat. Now, for the examples we've discussed, students and the example last week, that's really not such a big deal. Looping from 0 to 3 or 0 to 10 or even 0 to 1,000 is really not all that problematic. So why do you think that this constant resizing of arrays might actually be a bad thing? Right? Like, why bother introducing what seems to be more complexity, even though you could have solved this problem last week using the semantics of last week? Like, at what point does that approach to dynamism and growth become a problem, do you think? Yeah?
When time it takes to copy the array to a new array, like those.
Yeah, exactly. When the time actually starts to get noticeable, either to your CPU or worse, to the human. So a number of you have posted questions on the course's bulletin board about problem set 4 in Sudoku. Like, is it OK to exhaustively check the whole board, this 9x9 grid? That's 81 separate cells. That feels like a lot. But you, again, have a billion hertz at your disposal. You have a gigahertz, 2 gigahertz. You know, checking a 9x9 grid, that's really meaningless. And we saw as much when we talked about asymptotic behavior and we did some searches and sorts. For small data sets, you know, the running time is fairly negligible. But these days, and after a class like this, you're going to start playing with much more interesting data sets, whether it's because of computer science or you go back to your bio labs or your chem labs, where you actually have interesting sized data sets. Again, these naive approaches, these weak 2 approaches of just storing things contiguously in memory probably aren't going to cut it, because you're going to start to incur the costs of time, of space, of CPU cycles. All of that begins to add up. So how might we then go about doing this? Well, let's take a look. In this code is list1.c. And we have the following setup. Let's just glance at main for the moment. All right, so main looks like it's pretty simple here. Printf, I have some new lines. And this is a little trick. If you've never picked up on this before or haven't seen this in a text or a TF do it, if you have a multi-line string, it's not the best thing to call printf, for instance, 6 times here, because anytime you call a function, you actually incur a bit of cost because of all of the stack frame stuff we discussed. So you can actually call printf once, pass it a multi-line string, and notice I have not put semicolons at the ends of any of these lines, but I have closed the strings in double quotes each time. All right, so scrolling down, looks like I'm using CS50's library, telling the user to give me the command. I'm using the perhaps now familiar switch construct, though I could have used an if-else. I have 4 cases. I call a specifically named function in the case that we need to delete, find, insert, or traverse the list. And then again, we do this do-while construct because it's sort of a user interface. Well, let's see at least a hint of the notation here. It looks like I'm doing some stuff with pointers at the very end just to free the whole list. So that's consistent with this idea of managing our own memory. But how do you represent this linked list in the first place? Well, if you have an empty list, how can you represent an empty list? What primitive do you need? I've intentionally left the answer on the board. How do you represent an empty list? What do you need? Do you need a struct? Do you need to call malloc to represent a list of size 0? No, so you just need what? So a null pointer, where can you store it? Well, looks like in this program we've decided globally to declare a pointer called first. It's of type node star, and that just means this thing is just going to hold an address, but the thing it's going to point to is going to be a node. So that's all that's saying, and it's consistent with last week's definitions of pointers, and we're going to initialize it to null. Which is to say, in the context of a data structure like this, if we simply want to create a new list or represent a new list, we won't have had occasion to call malloc yet, so we won't have any valid addresses. So we simply need to declare 32 bits of memory. We will call this apparently first. And what's going to be inside of it? Well, unless we assign it a value, it's going to have junk in it. So that's why in this case we've initialized it to null. So that's it. So now think just conceptually. When I call the insert function, when I type in the number, what was it, 3, the insert function is called, and I type in thereafter the number 50. So that's what I did in the little demo a moment ago. What is the insert function probably doing? Step 1, the insert function, based on the behavior we saw, is doing what first? And just to remind, so if I run this linked list program and I type in 3, OK, what's it doing first? So it's doing a printf, and then it's doing, I'll only jot down the more interesting one, it's doing a getInt, right? It's probably using the CS50 library also. All right, and here's where I typed in 50. So what did it do with this value? GetInt, it probably stored it in, and I'll write slightly more complete code, it probably stored it in a local variable called n or whatever. So n equals getInt. This is probably the code that was just executed. All right, what did it probably do is step 2, when I then proceeded to hit enter, thereby putting a value in n. If the goal is, again, to construct dynamically one of these things called a linked list. Just conceptually, what did it have to do? Sorry? OK, so it's got to somehow set this pointer, which up until now is still null, to point to this value. So we can't, this is not a pointer to an int. So we cannot do, for instance, this. We cannot, if this is the int in memory, we cannot just have the pointer point to that int and no longer be null. Because what is this a pointer to? Not an int, but a node. OK, so how do we make that happen? If we need to have this pointer point to a node, and all we've got in memory at the moment is apparently an int, what do we need to do? Or who do we need to call? All right, so we call malloc. So we call malloc with something like this. I'm going to do a node star. So this is sort of C code, sort of pseudocode at the moment. So I'm just going to use ptr. This is a common variable name for people to use for pointers. So this gets what? I need to call malloc. And then what do I ask malloc for? One node? If I ever ask in that slightly sarcastic voice, the answer is no. So what do I put in here? Yeah, so size of node. OK, so we need to know, we need to ask malloc for a specific number of bytes. Now, maybe I know how many bytes there are in a struct. In fact, if I think it through, if a struct called node has an int, right, if it has an int and a pointer, I actually can guess how much space it's going to take up. How many bytes is a node struct? Can you infer? So it looks like it's 8, right? Because I need 4 bytes, 32 bits for the int, then another 4 bytes, 32 bits for the pointer, because all pointers are 32 bits in this environment. So that means 8 bytes. So I actually could, though a bit riskily, type in 8 there and actually get the number of bytes I need. But this is not a safe assumption to make, because it's not necessarily the case that the compiler or the computer is going to give you just 8 bytes. There are cases in which you would actually get back more bytes, and things would not be laid out as efficiently as you might think. So let's instead use this size of operator. I pass in size of what? Not int, but node. And now, dynamically, did I hopefully get back either a null pointer, but that's pretty unlikely given how few things I've asked for so far, or I'm going to get back the address of a chunk of memory that is now mine to manipulate. Now, this is just raw memory, but the neat thing is I can now treat it as though it is a node. Because the thing about C is that even though you're just handed sort of a chunk of memory that has no data type associated with it fundamentally, you, if you know how big it is, can just assume that you can treat it as the struct in question. So the fact that we're saying node star pointer means that the memory I'm getting back, even though it's just a generic address, I'm going to proceed to treat it as though it's the address of a node struct in memory. So now what do I do as step 3 most likely? I've now got n in an int. I've got an address of a chunk of memory that I can use for a node now. What do I need to do as the next step to create the beginning of this linked list structure? What needs to happen next? So here I have, just pictorially, this is my int. It's got my number in it. This thing's a little bigger because it has 2 fields ready and waiting for me. So what do I need to do? Yeah, so put the int into the node. So how do I do this? Well, we've seen, though not used it that much, this syntax before. If I want to go into that address and follow that address to the memory location, but I want to go to a specific field, the notation is this arrow notation. So I'm going to go pointer, arrow, and then the field I want to update was called what? Little bolder. N, right? So go to that address, go to the field I have defined as n, and then assign it the value, of n. Now, you might be recalling issues of scope, or you might recall when we had same variable names before, this was problematic. But this is OK, because the compiler very clearly realizes you want the variable called n, or the field called n, that's associated with this pointer, with this chunk of memory, whereas this n, just in this vacuum, clearly refers to the local variable that we're using here. And let me re-angle this if those of you on the side are having trouble. So there's one last step to clean up the memory I've just been given. So right now I've just now I have this. I have the same memory, question mark, but at the top now I now have whatever the value of n is. So let's put 50 in here. 50 is now also in here, but what's this? Just garbage value, right? Because it's just been a chunk of memory I've been handed. So step 4 is probably going to be to do what here? So create a null pointer. And it's probably not the best verb to use since you don't really create pointers. This is just a hard-coded value, a 0. But that's the right idea. The next field of this struct is just going to be null. And now what I have is something that looks like this, 50, and then a null field here. And actually, I'll draw it graphically. What most people do to represent null is just a backslash or some kind of angled slash in the box. OK, so now that's step 4. But I haven't actually created a linked list. At this point in the story, my linked list appears still to be empty. So the 5th and final step is going to be what here? What needs to happen now? So we're so close. We have this thing just floating somewhere in memory, and that's fine, because memory does not need to be contiguous for lists. This thing here is our global variable called first, which we initialized, per the code we saw, is initialized to null. So in order to literally connect these things, what do I need to do? Yeah, so assign first the value of pointer. So literally, the last step is first get, which is currently null. Let's overwrite the value of null with the address of this struct in memory. So pictorially, what I just did in step 5 is I changed the value of first to be from null to be something like OX123, or wherever this thing happens to be in memory. But that's not really interesting anymore, the specifics anymore. So let's just draw it with our familiar arrow notation. Now what I have is that. So to recap in step 1, this is old school stuff. Get the int. Step 2, allocate space for the structure that's going to store that int and another pointer, some metadata, if you will, so that we can string these things together. Then what do? Put the int into that structure. What do you do then? Put null in the next field of that structure so that you don't reach a garbage value and assume there's more things in this list than there are. And then finally, you just now need to link things together. Your list was previously empty. You now need to wire things together. So now what do I have in memory? Even though this thing's a bit messy on the board, let's spin it around for one final clearer picture. Our linked list now is quite simply first. And then we have the number 50 stored in a node here. This arrow points here. This is a null pointer. Voila, that's our linked list. Now, this felt like a lot of work, right? It's kind of easy to create an array with the number 50 done, right? We did that last week with just syntax like int, we'll call this array, bracket 1. Right? So we've just done a lot more work. But if we now factor out these concepts, these operations like insert and later delete and find and traverse, then you just have to call the function, hand it the linked list or have access to this first pointer, and then you can repeat these same operations again and again. And you, the programmer, no longer have to worry about how big this structure needs to be in advance, unless the user wants to really push the limits of reality and ask for billions of things, which again tends to run afoul of some real world limitations. So, any questions? So that was either really clear or really confusing, and I'm not sure which. So let me ask again. Any questions? Oh, that's good. All right, thank you. So I'm not sure you can see this, but thanks to Harvard's financial crisis, the temperature is intentionally being raised in these rooms. So I apologize for my appearance if you can see the glistening here. But let's now put you guys in the spotlight. So we're not going to use the clay. I'm not sure I could take myself seriously playing with Play-Doh in Sanders Theater. But if we could get 4 humans up here, you won't be playing with this. You complimented the clarity, so come on up. You're number 1. Someone else. Yeah, in front. 2. And you do have to be comfortable, yada, yada, on film here. 3, yep. And 4, come on, you stood up, so you nominated yourself. OK, so we've done things like this before, and I'm always amazed by how many humans are willing to actually come up here and do these silly things. But what I hope is that what we just did on the board is very easily forgotten. It's fairly esoteric, these kinds of low-level details. But let's see if a visualization doesn't make things a bit clearer. So let me go ahead, and I'm going to use 3 of you guys. How about the 3 of you just as a chunk of memory? So if you could just duck off to the side for just a moment. We're going to allocate you in a moment. I didn't really have a good way. And your name is again? Alex. All right, so you are a pointer. So you're a null pointer, and when you're a null pointer, let's just say you keep your hands, by your side there, but just don't point at anyone just yet. So you guys are a chunk of memory. So you are RAM. And now we'll start with small numbers. I decide here that I want to insert into this currently empty list called Alex a number 2. So I call getInt. I am handed the number 2. What's my next step? malloc, right? So I'm going to allocate memory. So I'm going to ask the operating system for, I need 8 bytes of RAM, please. Nominate who you will. OK, so I get back a pointer to, your name is?
Olga.
Olga. So I get a pointer to Olga here. She is 8 bytes of memory. I'm now going to do what with respect to our chunk of memory here? All right, so this is really not fun if we're the only ones playing this awkward exercise. So I'm going to store in the field called n, which we'll represent with our hands, just like Alex is doing, the value 2. And why don't we duck off to the side a little bit so we're out of the way of this stuff? OK, so now she has a pointer. And let's do your left hand is your value and your right hand is the pointer. Or actually, let's do the opposite. That way. That'll make sense. OK, so now we're at whatever we were. This was we just did step 3. So actually, we're almost there. So that's step 3, but we really don't have a linked list. We've got a null pointer, and we've got a chunk of memory, only half of which has been used in an interesting way by storing 2 there. What do we now need to do? Yeah, so we now need to store a null pointer here. So for dramatization's sake, can you make kind of like a garbage value with your left arm? So that's before. OK, and now we initialize your pointer to null. Excellent. All right, so it's working. First time we've ever done this demonstration in CS50. So we're figuring out as we go. So now what's the 4th step? Good. So actually point the first variable, that's right, to this new chunk of memory. So Alex, your time to shine. Excellent. OK, good. So now we've just recreated what we had on the board, albeit with a slightly different number. OK, so now things get a little more interesting, though, because now I get a little greedy, and I decide that I want to put in, say, the number 3. So I call getInt. I am handed by the user the number 3. Now I decide step 2 to call malloc again. So malloc away. Hello. What's your name?
Julie.
Julie. Julie is returned to me, or the address of Julie. She, too, has in her right hand space for an int. And in her left hand, what's in both of your, oh, this will embarrass you. What are your 2 values right now? We need you to represent 2 garbage values. Thank you. OK, so now we store in Julie's n field, in her right hand, the value 3. OK, what do we do for step, let's keep track for those following notes. OK, we just did step 3. Step 4 is to do what? Good. Assign null to her left hand. Done. And step 5, finally, is to have what? Alex point at Julie? Julie, right? Yeah. OK. No, right? OK, so what do we need to do? Where does she belong if the goal, to be clear, is a sorted list? All right, so here we need actually a bit more work. Here we need sort of a temporary pointer, so I'll play that role. And I need to sort of initialize myself to the start of the list. Well, what does this mean? Well, this really means I'm just going to point at the same thing Alex is pointing at. So now I'm going to check. Let's check Olga's n field. All right, is 3 less than 2? Well, no, so I'm going to keep going. Now, unfortunately, I'm pointing to nothing, which means I've reached the end of the list because Olga has nowhere else for me to go. And so this implies that this number 3 goes here. So now, very carefully, and we haven't walked through these steps, what needs to happen now to add Julie to the correct location in the list? 1 step, in fact. Your time to shine. Very good. OK, but we're intentionally plucking off some of the easier ones here. Now, finally, we're going to go with the number 1. All right, so things get a little trickier. So I call getInt. I store number 1 in my variable called n. I then call malloc. Hello, what's your name?
I'm Robert.
Oh, Robert, nice to meet you. OK, so now you look like what at this point in the story? That's great. OK, so now we assign this number to n, which goes in this hand here. Now, again, Robert, if I can drag you in this direction, you're anywhere in memory, right? So you could be here. OK. Yes. what? Can't see on the camera. OK, here. OK, so now Robert has his end field initialized. The left hand is still doing whatever. So step 4 here was nullify your pointer. Good. So now he's in good shape. So now it's my turn, the temporary pointer. And I have to have some kind of loop again. Maybe it's a for loop. Maybe it's a while loop. So I point where Alex is pointing. I then check, does Alex belong here? Aha, he does. Robert. Does Robert belong here? Yes, to the left of Olga. So now there's a bit of trickery. So let's see what we need to do. How would you, the audience, propose that we insert Robert into the right location here? What's the first step? By a show of hands, so we can actually pinpoint the voice. Yes, and back. Alex has to point to Robert. OK, Alex, please point to Robert. OK, now what? Yes, null point. So now dangling pointer, as this is called, because we've now lost Olga, we've lost Julie, which means you just cost us a lot of RAM. You have a memory leak. Your computer is now going to slow to a crawl, right? So, but thank you for playing. That's good. Let's roll back, right? Let's Control C, back up, rerun the program here, and now Alex is again pointing at Olga. We do this check. We realize, oh, Robert does belong to the left. Let's do a new first step. OK, so Robert points to Olga. OK, so Robert points to Olga. OK, looks a little weird, but maybe this is OK. Then what? OK, now Alex points to Robert. Now, this is actually realistic in that the memory can be all over the place. For visualization's sake, let's cheat and have Robert come over here, even though he really is anywhere in memory. But now notice what's neat. So that was actually a bad part of the visualization, because the compelling thing about linked lists is that you don't actually have to shuffle people around. And this was one of the problems initially with arrays, is that if you wanted to insert something into the middle, we had a problem, right? When we saw this with our searching algorithms and our sorting algorithms, if we wanted to put someone into the middle, we had to shift all of those people over. But as soon as we started shifting, we started increasing our running time, and we started devolving, if you recall, back to things that are quadratic and no longer linear. But yes, even though the humans here did need to make room for these, for the addition of Robert, technically they're just updating pointers. So the first pictorial with him way over there speaks to the fact that it's much more efficient to insert here because we don't need to worry about contiguousness of all of these elements. So a big round of applause if we can for these 4. You have a little parting gift here for you today. I'm not sure how you'll use this, but thank you. Let's take a 5-minute break. And Yuki will need to see you in the corner. Thank you.
I already signed it.
OK. All right, we are back. Kind of brings the fun to a crashing halt, because now we have some code on the board. So you have in your in the slides that I will leave available online, there's actually a number of depictions of what we just did with humans. So realize and refer back to this in a couple of weeks' time, because what this is meant to seed your minds for is for problem set 6, which is a little bit a ways away, but it's in problem set 6 you'll find that you're challenged with implementing the fastest spell checker possible. And we pretty much take off the training wheels at that point and encourage you and invite you to implement your own choice of data structure. And we haven't seen many yet. We've just seen linked lists, but you'll find that these linked lists from today will become a building block for much more sophisticated data structures that we do in 2 weeks' time. So these pictures, realize, walk you through the process of what just happened perhaps a little quickly with humans on stage. But what I'm going to do instead, instead of walking through this again and again, which is what we pretty much just did, let's focus on the actual implementation of this, because some of the syntax is new, but hopefully the concepts, once visualized with some people, is now a bit more clear. So this is the guts of the insert function. So you again have a printout of this. This is list1.c. Lists.h, note, actually has the definition, list1.h has the definition of the struct. So just to be clear, I factored it out to this header file, which again is pretty typical. Anytime you want to declare some data structures, or you want to create a file that other people might also use via sharp include. So here's the function insert. It takes no arguments, because we're going to ask the user for the number to insert at this point. But notice what I'm first doing. I've decided at the very start of the function called insert, try to instantiate a node for the number. Now I'm doing this because I know once I get a number from the user, I got to tuck it away inside of things. So the order of operations here is a little different than we did verbally, but we're going to cover the same steps. So the syntax for this is give me a pointer called new pointer. You could come up with most any variable name there, and it's of type, it's of type node star. So let me scroll back to that. So it's of type node star, which means give me a pointer to a struct that's of type node. All right, I'm calling malloc. I'm passing in the size of a node. And just to be clear, why not just hard code the number 8? Why incur the expense of calling this thing called size of? Yeah. In case you want to enlarge the struct. And again, even though this is more of a corner case, but we will see a taste of it in problem set 5, the forensics problem set, you're not, even though we draw n right on top of next, sort of back to back in our picture, that doesn't mean they're going to be perfectly back to back in memory. Now in this case, in reality, they probably will. But if we start creating data structures that don't have these 4-byte values, like an int and then a pointer, but maybe a char, another char, a float, an int, if you start to commingle lots of different data types, for efficiency's sake, what the computer will often do is word align, W-O-R-D, word align these values, which just means it's going to try, for efficiency's sake, to line them up every 4 bytes, which means you might have gaps. So another motivation for actually keeping track of this thing here via size of. So here's a little sanity check. If I get back null, just return. Now I don't bother in this particular demo to tell the user anything. I just ignore the user. So sort of is unfortunate, but we at least handled the return of null, because if you take a null pointer and try to follow it, you will in fact segfault. And that's kind of a feature of the language. Null is a constant that represents the number 0. The number 0 is a valid address in memory, right? That is the 0th byte of RAM. But the authors of C essentially decided that this byte will just never be owned by the user. So it will always trigger, for instance, a segfault so that you know there is a problem. So that's actually a good thing, having it initialized to some known value. So here is what our first step was. Printf, number to insert. Let me go ahead and get int. And I actually saved a step here. I didn't bother wasting the space for a local variable. I just plopped the int that the user gives me directly into the struct. Reasonable optimization, but achieves the same task. But then I do very carefully initialize the next field of my node pointer to null. So that's precisely what we did on the board and then pictorially here. Now I'm just going to check the 3 cases. So at this point in the story, we had Olga holding a number, and then we had Alex pointing to nothing. So we now needed to consider the scenarios. Is Alex pointing to something? If so, we're going to have to traverse the list. If he's pointing to nothing, that's actually really nice because it's really easy to code. If Alex is currently null, if the first pointer is null, well, this is so easy. First gets new pointer. Just make Alex point at Olga as he did, and then we're done. But there's a couple of other cases. Apparently, I have to check if the number belongs at the head of the list, the start of the list, or if it belongs in the middle, or it turns out you can model the tail, the end of the list, in pretty much the same way as the middle. And the only way you would realize this, frankly, is by actually thinking it through. This is not necessarily obvious. But let's go with the slightly easier case, right? I like 2 lines of code instead of several there. So case 2 is if the number we just inserted belongs at the list's head. So now fast forward to the situation involving Robert. Robert was number 1. He belonged to the right of Olga. So Alex would have to start pointing to him. So the case there, we had to update 2 things. And we didn't quite get it right at first, but we did subsequently. We first told Robert to point at first. Now wait, I'm a little confused. Isn't first Alex? Why does this actually work? What is first? First is a pointer. It's an address. What is the address of, to be clear? So it's Olga, right? So even though we talked about Alex as representing this first pointer, the value inside of him actually represents the address of Olga at that point in the story. He's just a container storing an address. So when I say that the new pointer's next field equals first, that means follow Alex's hand, which leads to Olga, and store that address inside that field. So it's the same thing, but just realize that Alex himself was not a node. Alex did not have 2 fields. He just had an address, which is why this direct assignment makes sense. Now we told Alex, go ahead and update yourself to be the address of this new node, that is point to Robert. So at this point, I'm not sure whether your mind sort of prefers the model of just thinking about things as arrows and humans pointing at each other, or if you prefer thinking in terms of addresses, this approach too is literally the translation of what we did in that demonstration. So if you're more comfortable thinking these things as addresses, that's fine. If you're more comfortable thinking them as arrows or hands, that too is fine. But now let's glance at the slightly more complicated case. And this is where, your brain gets a little squeezed because you have to very carefully consider how to do this. But thankfully, you do it once, and then your insert function works. So let's consider, ideally without getting lost, how we go about inserting into the middle of the list or to the end, the tail of the list, as we did with Julie in that second scenario. So what I'm going to first do is, this is apparently my role. When I came over here, I was pred pointer, a predecessor pointer, and I chose these variable names just to be consistent with that textbook's figures. I pointed at the same thing Alex was pointing at, so that highlighted line of code is exactly what I did as that temporary variable called apparently pred pointer. Now I just need an infinite loop, and it's OK to induce an infinite loop using for or while, so long as you are sure logically that you break out of it, if that's ultimately your goal. So I'm first going to check this. And we didn't bother doing this because I didn't print duplicates on paper. But I am going to check if the pred pointer's end field equals the new node's end field. Well, forget about this. I don't want duplicates in this list. And this is an undocumented feature of the demo we just did. This feels a little foolish, though. So some of you might notice I just wasted some time I'm allocating a node at the top of the file, at the top of the function using malloc, and yet this feels kind of dumb. Only then do I check for duplicates and deallocate this node by calling free. What would be an alternative to this? Because this feels like I'm wasting time. I allocate the node, and then I realize, damn, I don't need this node. Here it is back by calling free. What's an alternative to that approach? Yep. OK, good. So just intuitively, maybe I'll just do a pre-check. Let me run through the whole list, which is pretty easy to do with a for loop. And I did it just by pointing again and again to the humans on stage. Let me just do a sanity check. And if I see a duplicate then, maybe then I can actually quit. But now I've essentially doubled my running time, because if I do this pre-check, I have to linearly go across the whole list. Then I might say, oh, there's no duplicates. Now I have to find where to go. So that would work, but maybe we could do slightly better. And maybe better just means, you know what? Let me just allocate the moment I need it, this node, and don't do it at the front of the list. In other words, let me go ahead and copy these lines, and down here, when I actually needed the new node, I could insert this code here. But the reason I didn't is because I have these multiple cases. If I had done this approach, allocating this node on demand, now what do you notice me doing, which is generally a bad thing? Copy paste, right? Duplication of code. There's clearly now an opportunity to rip that code out, factor it out. So it's just a trade-off. And it's a design decision that one could argue, maybe either way. But generally, when you resort to copy paste, there's probably a better way. So at this point, we're going the right direction, it seems. I have my node. And maybe duplicates are a rare thing. So maybe we could argue that it happens so rarely, who cares if every once in a while we spend a few extra cycles. That, too, is a reasonable decision to make. So let's see. Check for insertion at tail. So there's two cases in this bigger case. Is it in the middle or is it the tail? After a lot of thought and maybe some trial and error, I realized it's a little easier for me to check for insertion at the tail. So if the temporary pointer, me, if I'm pointing at nothing, as I was in one situation when we were inserting Julie, then it's actually a really easy case. Go ahead and point the new structure to, point the end of the list, whom I'm currently pointing at, to the new node. And again, I won't dwell too long on some of the code, because I know it's very easy to get lost on some stupid little detail, and that's fine. Reasoning through it with the picture in hand can certainly help afterward. But this is just a translation of what I did to insert Julie at the end of the list when only Olga was there. The list was of size 1. So now let's assume, and we didn't do this per se, because we inserted Robert at the beginning, not at the middle, but there is this last case. So this is kind of interesting. You can actually chain together this arrow notation. If I am the temporary pointer, pred pointer, and I follow the next field, and then I follow the down into the end field, so I've kind of gone step, 2 steps. If that equals the n in the new node, I know that this node belongs somewhere in the middle, and so I need to update 2 pointers here. And again, I don't want to dwell so much on the syntax here, because I think it's best done just by drawing a picture on, say, the slides when thinking this through. But the takeaway that I think is interesting is that there just needs to be 2 pointer updates. So we've really only seen 2 general cases. 1 pointer update, which was terribly easy, and that's why we did those examples first, and that's why I myself coded them up first. And the only more interesting examples is when the thing belongs at the list's head, we realized that we needed to update 2 pointers in the proper order. And similarly, if it belongs in the middle, just conceptually, we've got someone here, someone here. Certainly, we need to update 2 pointers so that they point to me, and then I point to them. So this is the reason for this double traversal is that because once you go left, you can't go right in a singly linked list. A singly linked list, by definition, has only single lists going in one direction. So as this picture here depicts, this happens to relate to deletion, which is the same idea when searching through a list and then wanting to delete a node. What do we do? Let's actually do insert in the middle. And this is the one with several steps. If we want to traverse this list, notice, just as the arrows indicate, we can only go left to right. So it turns out sometimes, for programmers' convenience or for algorithms' sake, you can actually throw more data, more metadata into these structures. There's nothing stopping us from having not only a next pointer, but also a previous pointer. Because in fact, it would have simplified some of my code if I had the ability to traverse the list this way and then look backwards, because then I could have eliminated, if you look closely at the code come problem set 6, I could have eliminated one of my temporary variables. Because again, in that code, I had myself, and there's also another temporary variable that's essentially following what's going on in the story, a left hand and a right hand, if you will. But if I have the ability from any node to go left or right, can I then get rid of one of those temporary variables? But this, again, hints at this trade-off. Like, I can double my number of pointers, save myself some thought, save myself some logical coding, but the downside, of course, is now I'm spending twice as much memory on these pointers. But here's another question, and this picture kind of spoils the fun answer. How do you determine the length of a linked list according to how we've implemented it thus far, which is a picture more like this? How do you determine the length of this thing? Just traverse it, right? Start at the beginning, start where Alex was, and go da-da-da-da-da-da-da, following the arrows, and as soon as you hit what? Do you stop counting? The null. As soon as you hit the null pointer, which originally was at Olga and then at Julie, their left hand was null, then you know you're at the end. And so long as you've been keeping track with an int, plus, 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 you know that the list is, oh, it's of size 3. But that's a little inefficient, right? And here, too, is this trade-off. We could probably spend 32 more bits up front and actually avoid having to recount the length of this list. If I'm writing some program that constantly requires that I know the length of the list, why not just compute it on once and keep that answer around? And so what this picture also hints at is the fact that Alex did not need to be so simple. He did not just need to be a pointer to a node. He himself could have been an entirely separate structure, right? We've seen how to define a struct, type def struct, some name, and then whatever you want to put inside. So we could have made Alex a special struct that we just use one copy of. One of his fields is, in fact, a pointer to a node. But his other field maybe is, as this picture implies, an int, the size of the list. So what I could go do is go back through all of my code and go back through all of my demonstration, and every time I insert, say, Julie, every time I insert Robert, not only do I update the 1 or 2 pointers that are requisite for that, I also do what? To keep track of the current length. Then do the plus plus there. So again, this hints at, the opportunities that you, as the designer, as the computer scientist, have to solve problems more efficiently. If you don't want to waste time again and again, incur linear cost, just to compute the size of something, the length of something, you can solve that a priori by just keeping that information around. Well, linked lists are only one interesting data structure. And again, we will use these before long for a problem set. Another canonical example is this one here, a stack. And the cheesy example most any instructor gives when discussing stacks is to take some photograph of some trays like this in a cafeteria, because much like you experience as a human, when you put a tray on top, when say the folks running the dining hall put trays on top and top and top and top of one another, the last one in is the first one out. In other words, the top tray is the first one you, the customer, actually take off. So a stack is another data structure that is what's called a LIFO data structure, L-I-F-O, last in, first out. Now, this actually has some applications that you'll cover in courses like CS121, or even if you've ever written HTML, made web pages, you know that there's a structure to them. There's a hierarchy where literally if you indent things properly, even though it's not required, it gets deeper and deeper and deeper and deeper. Well, you can actually parse, you can actually analyze a web page for correctness and for other purposes using a stack. And the idea, just as an aside, is that each tag you read, you would push onto the stack, push onto the stack, push onto the stack, so that you have the most recent tag latest. And then you can check that all of your indentation and all of your symmetry is right by then just going backwards. But there's more useful purposes than just that. But this is a LIFO data structure. But all a stack is some chunk of memory that you can put something here, then something here, then something here, 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 here. But this is just a general data type, an abstract data type. How could you implement this idea of a stack? Using what C primitives or basics? Sorry? So we have a couple data structures at our disposal now. What's the simplest way to implement this idea of a data structure that just lets you put something on top of something on top of something? I mean, we've kind of done this, right? We just always drew the picture like this. Something and then something and then something and then something, right? It's just an array kind of flipped conceptually upside down, but there are some constraints. And here's the distinction. An array is really not an abstract data type. It's not a proper data structure in that you can just go anywhere you want. So in that sense, there's no, it's much simpler than the things we're now discussing. Whereas a linked list, you can't go to a random element. You have to start at the beginning, search through it, and that now has a more interesting cost. But with stacks, what is the only element in a stack, at least in reality, that you can access at a given time? The top tray, right? If you assume just one stack of trays here, the only one realistically you're going to get is the top tray. Going anywhere in the middle or the bottom just is not physically feasible generally. So the operations that a stack typically supports are something called push and something called pop. And these functions would just be implemented, whether using an array or even a linked list, to add or remove elements from this stack. But there's another one. So this is a silly picture of some crazy people lined up for the iPhone 3G in New York. So this is a queue. This is a line. This happens all day long. But this is, dare say, even more common data structure in computer science or in programming in general, because this data structure is a Fifo queue, a Fifo structure, first in, first out. That is, if you get there first at the front of the line, you're the first one to buy the iPhone. And this is has fundamentally different applications, right? Queues, or queues in this sense, this real world sense, are a much better solution to the problem of fairness than a stack. Imagine if you were one of those crazy people who wanted to get an iPhone that first day, and Apple, just because they're computer-minded people, decided to implement this thing as a stack. Right? You'd be kind of ticked off, right? Now it's... Right now, I mean, frankly, that is something like a computer scientist might actually do. But they went with a queue. And a queue similarly has insert operations and remove operations. But fundamentally, those operations manipulate different pieces of data. So when anytime fairness is important, queues are used. So in fact, though you might generally know that the internet has routers, these devices that take data from point A to point B, and they send them every which way. Well, routers have RAM, they have memory, they have hard disks often, so that when they get overwhelmed by traffic spikes, a lot of people downloading something at a given time, the routers can't handle everyone's traffic all at once, so traffic starts to back up. So thankfully, routers and many other devices have queues, chunks of memory, whereby a packet comes in and then it queues up. A whole bunch of packets come in, and when the router finally has a moment to deal with your data or your download, does it finally move you through the line. But here, too, there are interesting opportunities. You might know that some people like to prioritize on the internet, or would like to prioritize data like voice traffic, or they'd like to deprioritize downloads of illegal movies. And the ways you could do this are by using different data structures at the router level to actually prioritize different data. A queue is a pretty fair thing. But if you want some other type of traffic to go through that router first, a queue is not necessarily the right piece of the right data structure to actually deploy. So those are just teasers of some of the data structures to come. What I thought we'd do is end on this note. Very common at this point in the semester are bugs in your own code. We mentioned several weeks ago that one of the first bugs, or one of the most defining bugs in our history is this one here, when Grace Murray Hopper and her colleagues pulled out what was literally a bug from the Mark II computer and thus was entered into the notebook here, and they had a good laugh, haha, our computer actually has a bug. Well, there's been some stupid bugs too, and we are, the staff, are by no means guilt-free of this. We make mistakes, you make mistakes, and so what I did was kind of troll around for some inspiring, reassuring, if not humorous errors. This one you might have seen. How many of you have ever seen this on your own PC? All right, so this is the so-called blue screen of death. Not a terribly helpful message, but frankly, even at this point in the course, a fatal exception 0E. All right, I have no idea what that means, but ooh, hexadecimal. I can now understand a little bit more of this thing. Has occurred at 0028 colon some other stuff. VXD, that happens to represent virtual device driver. You wouldn't know that other than by Googling. But this was Microsoft's early on form of a really bad error message that, you know what, is actually useful. Just not to most of us in this room. In fact, really none of us, but to Microsoft's engineers, on the rare occasion you might be able to tell them what number you're experiencing, this is some kind of error code that's indicating a problem in this driver. Well, this one, too, is similarly arcane, but perhaps is a little more accessible. I have no idea what the problem was in this program, explorer.exe, but the instruction at 0x77ff, so that's an int. That's an address in memory, referenced memory at some other address. The memory, and this is the funny part, I think, the memory could not be read, as though to emphasize that. But this was just a bug in the program, and frankly, it sounds like it was some stupid pointer mistake. So if you ever do see this message, I mean, that's really what they're hinting at. This is just a bug in many ways. So this is like a legitimate error that someone took a screenshot of. Now things kind of devolve into less compelling ones. This is cute. This one, you have to think about it. That is true. So that is many years old and quite popular. This is just a problem. So this is within a browser using JavaScript, but bad things can happen even in that confines here. So this is just weird. So this is what happens when you start using Google Images too much. So this is a tattoo of a blue screen of death on this fellow's arm. He's still red from it. I don't know why. I'm a little uncomfortable with it, but we'll leave the slides online. So this too is bad, and I actually thought of this the other day. So this is Fidelity's investment bank on the corner of some street, maybe in New York. So that is a scrolling blue screen of death, essentially. An error has occurred and Windows has been shut down or something to that effect. And I wish I had had the foresight to pull out my camera at the time. I was just going through the subway the other day in Harvard Square, and those new swipe machines that they have for the entrance to the T. I was very sad to realize that whoever designed them, they use Windows to run those things because the little thing that normally says enter here said this. So that was kind of amusing. If you can catch a photo of that, do. So that we're being fair, though this one was actually kind of fun. So this was an advertisement for Windows Vista. The machine, funny enough, was behind glass. Macs are not infallible. This is the Mac's version of this. They've kind of simplified it. It's a little less scary than the blue cryptic message. Apple, in fact, doesn't tell you there's a problem. They just say, you need to restart your computer. Kind of cutting corners there. So this too, you start Googling, this is the sad Mac, which you Mac users get. I will not follow the link on the page I found this. Some people have done some sketchy things to their bodies involving error messages from computers. We'll link it on the website. This is from CentOS, a version of Linux. So this too happens sometimes. Please insert CentOS disk -99 to continue. But perhaps the best one of all time, oh no, second to best. This one I snapped myself. I was ordering pizza late at night. Being a geek, I thought a printf error was cool. So I was offered this upsell to buy some chicken in addition to my pizza. Do you see the mistake? This is a printf fail, right? They didn't use the right width for the floating point value. So this is $6.30, but they actually haven't padded it properly to have that 0. And this one is perhaps the most famous one. So some engineer somewhere years ago, maybe at HP or the like, decided that paper cassette load letter or PC load letter would be sufficient information for millions of people for 10 years to understand when it's time to load paper into the machine. We are perhaps not the only ones who find this aggravating. I thought we would end on this infamous note, slightly R-rated, but we'll end with this. We'll end with this final moment, a wonderful movie if you've never seen it called Office Space.
You know what I would do if I had $1 million? I would invest half of it in low-risk mutual funds, and then take the other half over to my friend Asadullah, who works in securities.
Samir, you're missing the point. point of the exercise is that you're supposed to figure out what you would want to do. If PC load letter, what the fuck does that mean?